Live. Okay, so today the topic is going to be rates of change.
Remember the kid who played the piano at that thing?
What?
Wait, what?
On Saturday, the kid who played the piano?
Yeah, the Frank kid,
He's
yeah.
a year younger than me. He's finished the whole calc series in college.
Yeah, he's a bright kid. Okay.
And I like to run.
That's all right. We all have our gifts, right? Okay, so define average speed. Okay, so average speed, think about this. You know this. If you want to find out what your average speed is, you could get your, so if you drive from here to Spokane, right, you could know then that your beginning time, you know your ending time, and so you take your distance, total distance, and divide by the time, right? But that doesn't mean that you just speed up, slow down, or whatever along the way. So it really is your distance 2 minus distance 1 divided by time 2 minus time 1, okay? Or if I rewrite that, d of t2 minus d of t1 all over t2 minus t1. Okay, now, it's a formula. It doesn't make any sense. It will in a second, okay? It's going to make sense. I hope so, okay? So, if you travel for 3 hours, right, then your distance might be 180. So your time 2 would determine your distance. That makes sense? If I travel for 3 hours, maybe it's 180 miles, right? Because how do you get 180 miles? Well, I just went, I plugged it in. So I plugged it. And this is your time 1, so let's say that at 1 hour I'm in Quincy, right? And so then my distance would be that. All divided by time 2 divided by time 1.
Wait, so both of them can work? Both of the equations?
Yep, both of those equations can work. This is just a little bit fancier in function notation, okay? So what you're really looking at, it looks very familiar. It looks like slope, doesn't it? It doesn't look like slope, and it really is slope. And slope is considered rate, right? It really is. Okay, net change. Now, net change is just the y values, okay? So it's just going to be your y2 minus your y1. Okay, that's just your net change. We're not worried about how much does it go up or down in any particular interval, okay? Or in function notation, f of x2 minus f of x1, okay? Same thing. If you plug in an x, you get a y. I'll say it again, right? I mean, we know that, right? You take an equation, if you plug in an x, you get a y. So that's a y. That's y2, isn't it? It's just weird, but it's still the same thing. If you take an x, you plug it in, you get a y value, right? So this is y2 minus y1, but it's in function notation, okay? So define average rate of change. So average rate of change is this divided by its x values, okay? So how much did you go up over a certain amount of space, right? So you increase by how much? Well, I can say, well, I increased by 100. Well, you did 100 miles, but I would hope you'd be asked, well, in how many hours, right? Or in cross country, Zoe, you ran 3 miles, great, and I'm going to say, what was your time, right? So we can get your average.
5 minutes.
So we can get your average rate. Does that make sense? So average rate of change is still going to be the same thing. We're going to have our f of x2 minus our f of x1 divided by our x2 minus x1. Sure looks like the slope formula to me. It really does. It really is. Or y2 minus y1 over x2 minus x1, right? Slope formula. We've done this. It's just a weird way of looking at slope, isn't it? But you need slope to be rate. It's pre-calculus. Slope and rate go together. They're synonymous, okay? So what's the average rate of change for a linear function? What's the average rate of change for a linear function?
Y over x. X over y.
It is y over x, yes. I'm looking for something. You're totally correct. You're totally right. But I'm looking for something a little simpler.
So that's definitely wrong.
What's the average rate of change?
Y equals mx plus b.
You're so close.
Y
What's the rate of change in this form, in this linear? What is it?
3 over 2.
Yes.
Wait, that's
Wait.
what?
So if it's the slope, you said it right, Landon, it is the y over the x, because if it's a rate, think about a straight line. Think about a rate. It's going up 3 over 2. That's a rate. Up 3 over 2, right? So a linear function, the rate of change is always just the slope, right? It's always going up 3 over 2, up 3 over 2. Now, curved lines is different, isn't it? Yeah.
It's not always 3 over 2, is it?
No, it could be whatever
Oh,
linear.
okay.
Give me any linear. Okay, in this example, okay?
What
Yeah.
about
Okay. Or Zoe, how about this? Y equals mx plus b. It's always b. How's that? It's always b.
That's M. You should go there.
It's always m. It's always m. It's always m. There we go. Okay, so let's take a look at the real notes so we can see it, okay?
The real notes.
The real notes, yeah. Which is this is just the first notes to get us caught up, okay? Okay. I'm sorry, Zoe. We love you. You know we love you.
Sure.
Yes, we do.
They do.
So let's hope we get you this time, okay? All right, so let's take a look at the real notes. Okay. So, example 1. The table below shows the outdoor temperatures on a spring day. Make a scatter plot. Well, I can do that. That's pretty easy. I'm going to get my graph paper out. You need graph paper. It's right over here. I'm just going to keep teaching, okay? So, scatter plot. Okay. All right. So, time. I'm ignoring it. Did I turn that thing off? Just leave it. Okay, they can, I don't know. Nine, 10, 11,
That's really annoying.
12. I know. Okay, now, when I do a graph with time, I shift it to military time. Because 12 points
What? It says no caller ID.
I'm going to change this to 13.
How do you know that?
I can see it.
Yeah. How do you know that? 13, 14, 15, 16, 17, 18, 19, 20. So this is the same as like a 1 o'clock, 2, 3, 4, 5, 6, 7, 8. Okay, right? And it's better to use because it doesn't make any sense to go from 12 to 1. Agreed? So I just use, military time. I'm going to do the squishy thing, which you've seen before. If I go squishy, think of that as being an accordion. I just squish the graph, and my lowest value here, I think, is 38. I think it's 38, isn't it? So if I start at 30, and I've got to go, how high am I going? To 50. So 30, if I go 40, 50, 60, right? You guys with me? So the squishy, I don't want all of them. Just collapse the graph, right? So let's do a scatter plot real quick. 8 o'clock, it's 38 degrees, so I'll guesstimate. Put a point there. Go and find a better pen. This will work. Okay, 38. And then I'm at 40, 44, 50, 56, 62, 66, 67, and now it's going to start dropping down. 64, 58, 55. Oh, I'm off, aren't I? Doggone it, somewhere around here. Here's my 67, 64. Yeah, I'm off by a little bit. Doggone it, I'm off. 58. There's my 58's there. 55 is there. There we go. Now I'm on. And a 51. Okay, there we go. And I can white that out if I need to, okay? All right, doesn't look linear, does it? Right? So that's easy. What's the first question say? Make a scatter plot, then find the average rate of change. The average rate of change from 8 to 9. So from 8 to 9, we go, and let me highlight from 8 to 9 so we can see it. From 8 to 9, I went up 2 degrees in 1 hour. Okay, so it's just 2 degrees in 1 hour. Okay, that's easy. From 1 to 3, so from 1 to 3, I'm going to go from 67 minus 62 over 3 minus 1. Okay, now I'm using my formulas that we took down earlier, right? Actually, use my formulas. There's my y2 minus my y1, right? Over my time 2 minus my time 1. I'm actually using my formulas, okay? Here's my y2. So it's going to be 5 over 2, right? Or 2.5 degrees per hour. Okay, that's easy. You guys agree? But actually use my formula, right? From 4 to 7. Okay, from 4 to 7. Here's 4 to 7. We're going to go, again, y2. So we're going to go 51 minus y1, which is 64, over 7 minus 4. Okay, I've got my y2 minus my y1 over my x2 minus my x1. Okay, so 6, 7, negative 7 over 3, or negative 2 1/3 degrees per hour. And the sign is important, isn't it? Having the negative, so we know the temperature is dropping, right? We know these are positive because the time is increasing, and all of a sudden the time starts to drop. So the negative is important in the context of the problem, isn't it? Okay? Not too bad? All right, so let's look at example 2. So fx equals x minus 3 quantity squared. Find the net change and the average change. So the net change, let's see, the net change is just the y's, right? So between 1 and 3. So let's go f of 3 minus f of 1. That's going to be my net change. That's my net, because the net is just what's the difference in the y's, right? So that would be, to plug in 3, I'd have a 3 minus 3 squared minus 1 minus 3 squared. Okay, all I did is I plugged in 3, my x2, right? Yeah, thank you, Zoe. I just plugged in here's my x1 and my x2, right? So I plugged in my second x value, because if we go back to our reading, that's what we saw, right? And then I'm going to get 0 minus, let's see, that's going to be a negative 2 squared is 4, so I get a negative 4. So my net change is it went from a height of 0 down to negative 4. Zoe, ask if you're confused.
What is in the first parentheses?
Oh, I plugged 3 right in here. So it's 3 minus 3 squared.
Okay, I just...
Yeah, good question. Please always ask, okay? This is our pre-calc class. We're going to take it slow and easy and make sure everybody understands, right? Nobody's going to be left behind, right? Okay. Yeah. And now if we want the average rate of change, we're going to take that, our negative 4, and divide it by 3 minus 1 between our intervals. So it went down 4 in 2, didn't it? It went down 4. So it went down 4 from 1 to 3. It went down 4 in a matter of 2 spaces, so negative 4 over 2. Our average rate of change is negative 2, okay? And that's like the slope between those two. And I'm going to give a visual of this when I'm done, okay? Now, from 4 to 7. So if I go from 4 to 7, same thing. I want to take my f of 7 minus my f of 4, okay? Plug in 7, plug in 4, right? So if I plug in 7, I'm going to have my 7 minus 3 squared minus my 4 minus 3 squared. This is my net. My net's just saying how much did the y's change. You with me? You getting the idea? So I'm going to go from 4 squared is 16 minus 1 squared is 1. So it changed 15 units. So it went from a height of 1 to a height of 16 is what it did. It went from a height of 1 to a height of 16, okay? So that's my net, but then my average rate of change, that's my net, but then my average is to go my 15 and divide it by my interval, which is my
Minus 1 come from?
4 minus 3
Okay.
squared.
And then where did the 15 come from?
7 minus 3 is 4. 4 squared is 16. So I'm subtracting now. So I subtract the 16 minus 1 gives me 15.
Okay.
You okay?
Yeah.
You sure?
Yeah.
Okay. So then it went up 15. It did. It went from a height of 1 to a height of 16. So it went up 15, but within what interval? Well, it went between 7 and 4. So it's 15 divided by 3, right? Which gives me 5. So what we're saying is it's 5 units per. Okay, now what I really want to do is take this darn graph and look at it, okay? So one way to do it is to put it on a calculator or decimals or whatever. So I just put it on a calculator because it's faster, okay? So if I graph this, let me just show you what we got going, okay? Because you need to understand what in the heck is going on. So let me go ahead and graph it, okay? So I've got my parentheses, I've got my x, subtract 3 squared, right? My window, we're only going between really 1 to 7, right? You guys agree with that, 1 to 7? So if I put in my window as, say, a 0 to 8. I'm going 0 to 8. Because what I want to see is 1 to 7, right? My interval is 1 to 7 from here to here. So I went 0 to 8 so I can see more of it. Okay, now I know the height of this last one was as high as 16. So I'm going to make sure I'm at least to 16. Maybe I'll make that up to 20. Let me graph it, okay? Okay, here it is. So let's see what we got. So first of all, first question was our net change from 1, check it out, from 1 to 3. Our net change went from this height to this height, right? And we found out the net change was negative 4. So it dropped from here to here to negative 4. Does that make sense? And then we asked ourselves, well, then what is the average? Well, the average is from here to here, negative 2. So that means it kind of has an average drop 2 over 1, drop 2 over 1. But it doesn't really do that because it's a curved line, right? So I like to give the analogy, it's like driving to Spokane. If we drive to Spokane, sometimes we speed up, sometimes we slow down, sometimes we stop and have coffee, and sometimes we have a bathroom break. But overall, we haven't. So it's like an average of going down 2 over 1, down 2 over 1. Got it? And then if we go from, what was it, 4 to 7. 1, 2, 3, 4, we're here. 4 to 7's up here, right? We jumped up a lot. We went from a height of 1 to a height of 16. So we went up by a height of 15. Does that make sense? And our average was 5. So in a sense, from here we're going up 5 over 1, up 5 over 1, up 5 over 1, up 5 over 1, which is not really what's happening. But over the long run, over the average, it's a rate of 7 per 1. In a sense, per hours or per unit, okay? Does that help give you an idea of what we're talking about? Okay? Now, we're going to learn, hopefully, someday, how to get the slope on a curved line. Actually, you kind of know it because we've been doing it, right? That's our f of h, a plus h minus f of a divided by h. That is going to be the curve, okay? All right, turn the page, all right? Now, here was what Newton was working on, okay? So Newton drops something off and he goes, okay, well, I can get my average rate of change. How fast is it going at any instant, right? So negative 16, okay? This should be a negative 16 d of t. I need to fix this. It should be negative 16 t. It has to be negative because gravity is going down. You agree? Has to be negative. And that's gravity in feet per second, okay? So find the average speed from 1 to 2, okay? So we're going to go d of t2 minus d of t1 all over t2 minus t1, okay? First distance, second distance, minus the first distance divided by the interval, okay? So that's no problem. So if I plug in, so I'll have a,
Can you slide it up?
yeah, sorry you guys. So what I want to do is plug in 2 first, because that's time 2. This is t1, and this is t2. So let's plug in our time 2 first. So we plug in the 2, right? And then we'll plug in our 1. So that's easy. If we plug in our 2, we'll go 16 times 2 squared minus 16 times 1 squared all over 2 minus 1. Now back up and let you take a look at it, okay? So I need the distance 2, plug in 2. Now it'll tell me how far it dropped in 2 seconds. I need distance 1, plug in 1 second, and that'll tell me where it's at after 1 second. So just divide it by the interval, okay? So do the math. I think I get 64 minus 16 over 1, which I think is 32, right? 32, oh, these should be 6 negatives, doggone it. It won't make any difference, we just need a negative here. Negative, pause, there we go. It has to be negative, because it's dropping. So this tells me the average velocity. This is my average velocity. The darn thing is dropping at an average of 32 feet per second. But of course, we all know that things can go faster and faster. You're dropping it, right? You know it's going to go faster and faster. But over the average, you can say between 1 to 2 seconds, its average speed is 32 feet per second. Okay? Now, let's take a look at the next one. So now, what if you were Newton and you wanted to find out the instantaneous velocity, okay? All right, so what did Newton do? He plugged in A plus H and A. So if I take a look real quickly at the graph.
64 plus
This one-
17 is 48. Don?
Oh, is it 48? Yeah, it is.
Good job, Sky.
Thanks,
I
Guy.
was like, wait a minute, what am I doing wrong?
No, nothing. Negative 48 feet per second. Thanks, Guy. I get ahead of myself. Okay. So, now, this is so cool. This is what Newton did. I'll give you a rough graph of it, right? So let's say he's on top of the Leaning Tower of Pisa. Let's see, what would have been a great feature? Newton was English, wasn't he? Big Ben, okay? And he drops something off the bridge, right? And we know it's going faster and faster and faster. So he wants to know the exact. So if he wants to find, because it is going faster. So Newton came up with this idea. You've got time 1 and time 2. Time 1 and time 2. And if you slowly bring these two together, it's no longer an average. The closer and closer those two times get together, the better your average is. Does that make sense? And this is physics, okay? So bear with me. Okay, so if you wanted to go, this would be an average velocity. The closer these 2 points get together, the more accurate your slope is, because it's a curvy line between the two. So this is what Newton did. We've done this. So Newton said, okay, let's plug this in. So I'm going to have a negative 16 times a plus h squared minus a negative 16 times an a. And then that would give him his net. But what if he wanted the exact? Then he'd say, okay, well, we would take my a plus h minus my a. All right, so what did I do? Okay, we've done this problem before. We have.
When?
Our last quiz. We plugged in a plus h. We plugged in a, and then we divided by h. The reason we divided by h is because those cancel, right? So let's do the math. So if I do the math, and again, just to shortcut this because I'm running out of room, hopefully you guys all know this. So a plus h squared is a squared plus a 2ah plus an h squared. Remember that? Do you mind if we shortcut this so we have less work to do? Because we've done this problem lots of times, right? So I'm going to go, okay, here I'm going to have a negative 16 times an a squared plus a 2ah plus a h squared plus a 16a all over h. Okay, so what did I do? I'll scoot up. Yep, I'll scoot up and tell you what I did. What did I do? I'll let you catch up. I know what this is, right? We have that. We've done that several times, right? If I FOIL it out, we've FOILed this problem before, right? A squared plus 2ah plus h squared. Okay, we FOILed it. I'm just making a shortcut for myself. I plugged in a, but minus and minus makes a plus. These two cancel and look with h. Now this should look familiar. You just took a quiz on this on Friday, right? Does this look kind of familiar? Maybe. I hope so. You did. You guys all got an A on this problem. Okay, and then what happens? Well, if I bring through the 16, I'd have a negative 16a squared. I'd have a minus 32ah. I'd have a minus 16h squared plus 16a all over h, right? So then I can,
Have 16.
that should be square, right? How come that's not square? I did make a mistake. This is a big deal. Okay, that cancels, that cancels. Have I lost you?
Yeah, like a long time ago.
Okay, let me finish the problem. I'll come back to it. Yeah, Sky?
One question, how do you get negative 16 from the first part? Yeah, right there.
I had to change, it is negative 16, right? Okay, so then, we've common factor out the h. Remember how I did that before? I took out the h. I'd have a negative 32a minus a 16h all over h, and the h's cancel, okay? So, my answer then is a negative 32a minus 16h. That's my answer, okay? How did that help Newton? And I'll come back and I'll try and explain it to you. How did that help Newton, okay? A is any value, any time. So if A is any value, let's say A happens to be 3 seconds, right? You plug 3 into here. Well, 3 times negative, what's that, negative 96? We'll plug 3 in. H goes to 0. Why does H go to 0? Because these 2 points get closer and closer. And then Newton got the exact velocity at 3 seconds. So he found a way to find the speed of an object at any particular moment. All by doing this, just the slope formula, okay? All right, want me to back up how I did this? Want me to back up? No? All right. Okay, now, example 4 is super easy. We're not going to make it hard. Find the average rate of change. Zoe,
What?
this is when we were giggling at you, but we weren't giggling at you. We were laughing with you. Okay, so let's think about this, okay? Average rate of change. Don't do the work. I know the answer to this, and I know the answer to this. Don't do the work. I already know the answer. So, if it's a straight line, what's the slope?
3.
So what will be the rate?
3.
Yeah, so you can do all this work and say, what's the rate between 3 and 7?
3.
It's going to be 3, right? What's the rate anywhere on the curve? It's going to be 3. So as long as it's a linear, then the slope will never change, right? If the slope never changes, then the rate never changes. So that if it's a linear, then we could do all this work, but guess what the answer is going to be? The rate is equal to 3, or the average rate of change is 3. I mean, you can do the math if you want to do the math, but the answer is going to be 3. Okay, that was